So the next topic that we have to learn after the completion of the empirical formula is the equivalent concept or the law of chemical equivalence. In mole concept, for example, if I take the reaction of say H2SO4 with NaOH to give sodium sulfate and water. If you want to apply the mole concept, you need to know the balanced chemical equation. Without knowing the balanced chemical equation, you cannot solve the question using the mole concept, because if you are given that the mole of H2SO4 taken is 1, that is 98 grams of H2SO4, it can be known how much of NaOH will react with it. So, for every 1 mole there are 2 moles that have reacted. So, therefore, certainly here 2 mole of NaOH, that is 2 into its molar mass. So, based on this ratio only one can ascertain how much of the other substance has reacted or how much of the product is being formed. Now, suppose if you want to look at how many grams of water is obtained. So, for every 1 mole you would say 2 mole of H2O is obtained. Indeed, you have taken 1 mole here. So, you are getting 2 mole. 1 mole is the molar mass. So, total you are getting 36 gram of H2O. So, here if you want to see how many gram of the other substances or how much volume of the other substances has reacted or produced, in order to know that, you need to know the stoichiometric coefficients. So, this is the beauty of the mole concept. But when it comes to the equivalent concept, now when we are applying this, is all about the mole concept. Now, when we are learning the equivalent concept, it is said that the gram equivalents, here you have been mentioning the gram mole, whereas here the gram equivalents of the substances reacting is equal irrespective of their stoichiometric coefficients. So, no matter whether you balance that equation or not, the gram equivalents are equal. So, here you could see clearly, when you have been applying the mole concept, you have seen for every 1 mole of H2SO4, the number of moles of NaOH reacted is 2. So, the ratio is never 1:1 when you are writing the mole, whereas when you are writing the equivalents of the same substances, that is H2SO4 and NaOH, not only H2SO4 and NaOH, any 2 substances which are reacting with each other during the neutralization process, the gram equivalents are always equal, or their equivalence ratio is always 1:1. So, here when you extend this further, you will find that the equivalents of all the substances that are reacting with each other are same irrespective of their stoichiometric coefficient. So, the biggest advantage of the equivalent concept is that we need not balance the equation every time, as the reaction that we will be seeing in volumetry are complex. Now, we need to find out what exactly are the gram equivalents. As we all know that the gram moles are obtained by dividing the weight and molecular weight. Now, when we try to find out the gram equivalents of a given substance, in gravimetry the gram equivalents are calculated by taking the ratio of the weight of the substance with the equivalent weight. Now, as we all are aware that to get the gram moles or gram mole, you have to divide the weight with the molecular weight, because molecular weight many grams of a substance is equal to 1 mole. So, W grams of the substance measures how many mole, that is weight upon molecular weight. So, here there is a new term that has been introduced, is nothing but the equivalent weight. Now, to get the clarity about the equivalent, to put this as aside for the time being, it has been said that the equivalent weight of a substance or an element is the amount which would replace or react with either 1 gram of hydrogen or 8 gram of oxygen or 9 gram of aluminium or 35.5 gram of chlorine. So, we say here that equivalent weight, I mean if you are taking the equivalent many grams of a particular substance, it can replace any one of these particular amounts of the elements. So, it may replace 8 gram of oxygen or it may replace 9 gram of aluminium. So, to get the clarity further, we will write the equivalent weight in terms of the atomic weight or molecular weight upon a term to be introduced known as n factor. So, in order to understand the equivalent concept, we have to get the detailed information about the n factor. Now, one has to learn that n factor is not a constant. N factor can never be 0. N factor can never have the negative value, but it can be a. This cannot be negative, this cannot be 0, this cannot be constant, but it can be a fraction. At the same time, the definition for the n factor from compound to compound differs. Now, let us categorize the elements or compounds into various types and define the n factor for each case. By knowing the n factor, by dividing its molecular weight or atomic weight, we will be finding out the equivalent weight. Once you can find out the, if you can find the equivalent weight, you will be finding out the gram equivalents. Now, the n factor of an element, the first category is the elements. The n factor of the element is nothing but its valency, its capacity or its tendency to form the bonds or the number of bonds that are present in a given compound. So, if you are taking the elements, let us see the element, its valency or the n factor, hence we will be finding its equivalent weight. Now, suppose your element is hydrogen, valency is 1, equivalent weight of that element is atomic weight by valency. If you take the element say oxygen, its valency as we know is 2, atomic weight by 2 will give you its equivalent weight, which is 8 gram. Now, that is why we have said that the substance can replace 8 grams of the oxygen, because it is reacting with 1 gram equivalent of the oxygen, and I told you that the gram equivalent of two substances that are reacting is always equal. Now, if you take further, if you take magnesium, its valency, ionic valency is 2, so 24 by 2. If you take aluminium, it is going to be 3, 27 by 3, which we have quoted as 9 grams. If you take chlorine, it is 1, so it is 35.5 by 1. So, that is why we said your element which is having 1 gram equivalent or E grams of substance can replace 35.5 gram of chlorine. Now, this is the definition for the element. Now, when it comes to the ions, it is simple that the n factor is nothing but the charge present on it. So, if you take generally the ions, chloride ion 35.5 by 1, carbonate ion, I am writing straight away the equivalent masses here. Carbonate ion, as we all know, its molar mass is 60 upon the formula mass rather charge. If you are writing SO4 minus 2, 96 upon 2. If you are writing HCO3 minus, so which is 61 by 1. Say you are writing ammonium ion, its molar mass or formula mass upon the n factor. N factor you can see straight away is the charge, the amount of the charge that is present on it. So, this is about the n factor of the ions. Now, moving further, when we enter into the compounds category, elements, ions appears to be pretty simple. When it comes to the compounds, in that when we try to define the n factor of the acid, we just say that it is nothing but the basicity, which is going to be the n factor of the acid. That is the number of replaced hydrogen atom. Please understand, we need to see how many hydrogens are replaced by the corresponding base when reacts with the acid. Then looking out for the total number of hydrogens. It may have 2 hydrogen, but it may lose only 1. Then in that case, the n factor is going to be 1 but not 2. So during the complete neutralization, if all the 2 hydrogen atoms are removed, then n factor will be 2. So if you take for example, say assuming that complete neutralization takes place, the replaceable hydrogen atom is 1, is 2, is 3. If you take this weak acid, it's going to be 1, because this is something which is attached to the oxygen, which is more electronegative, but not these 3 hydrogen atoms which are connected to the carbon, which is less electronegative. So here the n factor should be taken as 1 but not as 4. When it comes to the other example, similar example like phenol has 5 hydrogens attached to the carbon, whereas only 1 is attached to this. Now there are some complex examples like H3PO3. Although it appears to be that it is having 3 hydrogen atom, we have to understand that replaceable hydrogens are only 2, because one such hydrogen is attached to the phosphorus, which cannot be removed being less electronegative element. So the maximum n factor possible for this orthophosphorus acid is 2. Now there are some peculiar cases like orthoboric acid, which is not a protic acid first of all. Now let me explain why. You can see here that this boron is having total 6 electrons only in its valence shell. The reason being, the total electrons that are present with the boron in the valence shell before bonding are 3, and 3 more are obtained from the oxygen. So total is only 6. So this is always hungry for the electrons, acting like a Lewis acid but not a protic acid. It is not going to donate a proton. So now when this is reacting in a certain reaction, say the orthoboric acid reacting with sodium hydroxide to give you the borax, if you have been asked to find its equivalent mass, we have to write its n factor. Its molar mass is suppose m. So now we have to understand that being a Lewis acid, it will always form a dative bond with water, leading to the formation of a complex in which boron bears a negative charge and oxygen a positive. Oxygen gets positive because of its lone pair loss. Now in order to compensate that, it is going to accept the bond pair from the hydrogen, converting into this complex species, where you would see that the total number of hydrogen that are coming out is only 1. So during the calculations or during the finding out of the equivalent masses, we will be taking the n factor of orthoboric acid as 1. So this is one complex example. Now moving on to the next type of compound, they are bases. If you are talking about arrhenius bases, it is nothing but the acidity. So how many OH minus ions are going to neutralize the acid is going to be the n factor. So if you take amphoteric substances like aluminum hydroxide, H2O, the situation will be dependent on its behavior. For example, aluminum hydroxide is acting like an acid. The same situation persists or prevails, where the n factor should be taken as 1. That means in its reaction, NaOH, where it is acting like an acid because it is reacting with a strong base, its n factor is going to be 1. Whereas when it is acting like a base, say it is reacting with HCl, we have to count the total number of hydroxide ions. So n factor is going to be 3. In any case, the H plus or OH minus coming out of this is 1. So, N factor of water is always taken as 1. Let us find out the N factor of the salts. The next category is the N factor of the salts. The N factor of salts is actually the total cationic or anionic charge, because we are speaking about the neutral salts which are not undergoing any sort of redox reactions. So, the total cationic or anionic charge should be taken as the N factor in the double displacement reactions. These reactions are usually non-redox reactions. I mean to say there won't be any change of oxidation state of any element during the reaction. So, these reactions are normally observed when the aqueous solution of one salt is mixed with the aqueous solution of another one, giving rise to the precipitate usually. So, in such cases the precipitate is being formed along with the other salt which is soluble. So, I will take some more examples like sodium sulphate reacting with barium chloride to give you the barium sulphate precipitate and sodium chloride. Say you have taken aluminum nitrate reacting with barium phosphate in order to give aluminum phosphate and barium nitrate. So, in this case, as we have defined, you could see clearly that there is no change in the oxidation state of any element or the major element in these reactions. So, just the cation anion interchange has taken place. So, therefore, these reactions are double displacement reaction which usually occur in water. So, now the N factor of the salt is the total cationic charge equal to the anionic charge, because they have taken the neutral salts. So, N factor is, there is one sodium and charge of each is 1. So, likewise 1 silver, 1 sodium, and here 2 sodium, 1 barium, each carrying 2 units charge, 1 barium 2 unit positive charge, 1 unit positive charge. Now, 1 aluminum is carrying 3 unit positive charge. You can see clearly that there is a distinction. Now, 3 barium each is carrying 2 unit charge, hence the total is going to be 6. So, the N factor of barium phosphate is 6. Likewise, it is 3, this is 2. Now, based on this N factor, we can balance this type of simple reactions very easily, because the ratio of the N factors is always reciprocal to the mole ratio. You can see here this is 2:2 or 1:1, this is 2:1 or 1:2 is going to be the mole ratio. So, we say or we conclude that N factor ratio and mole ratio are always inverse to each other. So, here it is 3:6 or 1:2 is the N factor ratio of these two substances which are reacting. So, their mole ratio is going to be 2:1. So, here their N factor ratios are 3:2, mole ratios are going to be 2:3. So, this is one way of balancing the chemical reactions.